Good afternoon, everyone. My name is Mei Li, and I'm delighted to be presenting today alongside Anjali, Desai and Briana Geiger. We are students from School of Engineering and Computer Science at Auckland University. This research was conducted as a team effort with contributions from Professor Huirong and Dr. Rui Zhu. In this presentation, we'll dive into one of the most pressing challenges in cybersecurity today: AI-driven deepfakes, how they are created, the risks they pose, and the cutting-edge solutions being developed to combat them. This is a quick overview of our presentation. We'll start by introducing deepfakes and generative AI, followed by how deepfakes are technically created, and we'll analyze their security impact, review current detection systems, and share insights from our research on how these systems can be improved. We'll also look at a few case studies and end with our conclusion. In recent years, the number of fake videos, news, and images are not only increasing, but they are also getting more realistic than ever before due to deepfakes. So what are deepfakes? They are a form of AI-generated media can change images, sounds, or videos to create highly realistic but fabricated content. Deepfakes have the potential to manipulate and threaten individuals, corporations, or governments, raising significant concerns in the field of cybersecurity. At the heart of deepfake technology lies a powerful AI framework called Generative Adversarial Networks, or GANs. Here's how they work. Deepfakes utilizes two neural networks, generator and discriminator, which together make up a GAN architecture. The generator creates new fake images that closely resemble real data, while the discriminator tries to distinguish between real data and the fake data created by the generator. Through continuous competition, where the generator improves its fakes to trick the discriminator, and the discriminator gets better at catching them, the system produces outputs so realistic that they can deceive both humans and machines. Beyond GANs, deepfakes also leverage autoencoders to analyze and swap facial features frame by frame. This is not just about altering pixels, it's about replicating expressions, lighting, and even micro gestures with accuracy. Deepfakes weren't even a term until 2017, when a Reddit user shared AI-generated face swaps. Today, they've evolved into synthetic media. The accessibility of deepfake creation tools has lowered the barrier for malicious actors, enabling everything from credential theft, disinformation, and even cyber attacks. One of the biggest challenges is that deepfakes can bypass security systems, especially those that rely on facial recognition or voice authentication. Even more concerning is how they erode trust in digital content. If we can no longer believe what we see, hear, verifying truth becomes incredibly difficult. With this background in mind, it's important to examine the broader implications of deepfakes, particularly the serious security risks they introduce in various sectors. In politics, deepfakes can be used to spread false statements or stage videos of public figures. This can damage reputations, erode public trust, and even influence election outcomes. In finance, scammers have used deepfakes of CEOs to mislead investors, commit fraud, or spread misinformation to manipulate markets. On social media, fake or altered content can be used for cyberbullying or harassment. These videos spread quickly, often going viral before they can be taken down. And finally, in cybersecurity, deepfakes are now being used for social engineering attacks. They can mimic someone's voice or face to bypass biometric systems, enabling identity theft and unauthorized access to security systems. Deepfakes are making social engineering attacks more convincing than ever. Attackers can use techniques like phishing, impersonation, and pretexting to trick people into sharing personal or confidential information. Now with deepfakes, these attacks feel more real, such as hearing a fake voice messages from your boss or seeing a video that looks completely authentic. For example, phishing emails may look like they are from trusted companies, urging users to click links or share sensitive data. When people fall for these, it can lead to loss of data confidentiality, system disruptions, or even compromised integrity of entire network. Deepfakes play a major role in the spread of disinformation, posing serious risks to media integrity and democracy. They've been used to create fake news and even deepfake pornography, all of which can cause real-world harm. One example is from Slovakia election in 2023, where a fake audio clip of opposition leader Michał Samaska discussing election fraud went viral. Although it was later confirmed to be fake, the damage was already done. The clip spread rapidly across social media and may have influenced public opinion and election results.
Vulnerabilities. Deepfakes exploit vulnerabilities in AI systems, media platforms, and authentication. There is a lack of standardized tools to reliably detect synthetic content. There's a heavy reliance on biometrics such as facial recognition or voice recognition in banking and security. Voice cloning can bypass biometric authentication. Machine learning detection methods show 98% accuracy on similar datasets. Accuracy drops to 50% on unrelated datasets. Next, we have evaluation of existing deepfake detection systems. This focuses on machine learning models, which has 4 categories: model, components, its strengths, and limitations. We have the autoencoder, which consists of encoder-decoder architecture. It compresses and reconstructs faces effectively. However, it cannot produce highly realistic or sharp images. Next, we have variational autoencoder, VAE. It is an encoder-decoder with probabilistic encoding. It is better at handling facial variations. It is less realistic compared to GAN-based approaches. Next, we have generative adversarial networks again. It consists of generator and a discriminator. It generates realistic images through adversarial training. However, it requires intensive training and large datasets. Next, we have a GAN and VAE hybrid, which consists of both generator and an encoder-decoder. It combines the strengths of both models, improving realism and handling variations. It is complex and computationally intensive. Lastly, we have the EAR SVM, EAR with temporal windowing, and SVM with decision boundary learning for classification. It effectively captures temporal emotion patterns and provides accurate classifications using SVM. However, it may struggle with real-time processing and requires careful feature selection to avoid overfitting. Next, we have blockchain for deepfake validation. Public blockchain provides decentralized, tamper-proof verification of media content. It leverages cryptographic hashes to ensure content authenticity and trace its origin. Strengthens trust, accountability, and resilience across digital ecosystems. We also have Hassan and Sal's framework, blockchain-based design for verifying the origin of digital content, integrates decentralized storage, IPFS, and Ethereum named service for management, maintains transparent transaction records even after multiple copies and transfers. Chan's approach utilizes LSTM and CNN models for hash encoding of content features, stores encoded data on permissioned blockchain with owner-controlled access rights, enables detailed provenance tracking for image and videos. Next, we have limitations of blockchain in combating deepfakes. There's scalability and adoption, which remain key issues for widespread use. Consensus algorithms can be slow and costly for content creators and media companies. No universal standard exists, requiring global collaboration for integration. Blockchain needs AI tools to detect deepfakes effectively. High energy use poses environmental and cost concerns. Next, we have an overview of AI-based deepfake detection tools. There are many deepfake detection tools available online, including the following. Fake Catcher, developed by Intel and offering 96% accuracy. It uses a deep learning approach and biological signals that detect vein color changes to detect deepfake videos. Syncity AI detects deepfake audio, video, and images with 98% accuracy using pixel and voice patterns. True Media detects deepfake social media content via URL with 90% accuracy using integrated technology. Hive, which detects deepfake images or videos and provides a confidence score. It is trained on a high-quality dataset, which is free to use. Haya detects deepfake videos or audios using deep learning solutions with 99% accuracy. Deepfake, an ongoing research project to create the best machine learning solution for deepfake detection, training on adversarial examples and multiple detection methods that analyze inconsistencies between video frames and fakeness in audio. The project's goal is to help journalists in combating misinformation with a user-friendly, accurate tool. Next, we have strengthening deepfake defenses, AI robustness, public awareness, and policy interventions, combining different machine learning approaches to create a shared framework, adversarial training on models to increase accuracy rates, real-time integration of models with social media, media literacy programs to teach the public about the dangers of deepfakes, MFA and zero trust models should be enforced. New laws need to be enacted regarding the use of deepfakes and the privacy concerns of training models on real data.
This is the process of embedding the watermark. If we want to embed a watermark into an image, we take the host image and the watermark and segment them into blocks. We then change the image into the quantum domain using flexible representation of quantum images, or FRQI, in the Taylor series. Putting the result through the rotation gate creates the watermarked image. This is the process of extracting the watermark from the host image to verify its authenticity. We can take an image and convert it to pixels using FRQI so that we can process the image and its watermark on the quantum computer. After we finish extraction, we should reconstruct the watermark and embed it back into the host image. Quantum watermarking provides strong authentication of media content, showing whether or not something is fake. It is tamper-resistant. While the watermark on the image is imperceptible, if anyone attempts to modify the watermarked image, it will be noticeable. The watermarking technique was tested on different grayscale host images using Taylor series orders. Performance was analyzed, revealing that quantum watermarking could achieve high imperceptibility and robustness for detecting fake images. Some limitations of quantum watermarking are that its effectiveness is highly dependent on the host image structure, and that this is a very new technology that is still being actively researched, so it has only been tested on classical systems, which differ in how it may be used in real life. It is also limited by the current quantum hardware availability. Current detection systems remain vulnerable to adversarial attacks that target machine learning models into misidentifying fake content as real with small imperceptible changes. These models must have adversarial training done in order to increase the resistance to these attacks and retain high accuracy rates. We need high-quality standardized training datasets and shared frameworks to create the most reliable detection systems. Working together through cross-sector collaboration between tech companies, policymakers, and researchers is essential in achieving this. The general public is often very unaware of how realistic deepfakes can become and the dangers of them. Launching media literacy programs that teach people about these dangers and how to watch out for potentially fake information they see online is more important than ever. Additionally, stronger authentication protocols like multi-factor authentication and zero trust models should be enforced in every organization. New laws regarding the use of deepfakes have been recently enacted as they become more and more widespread. In the US, the Take It Down Act criminalizes sharing non-consensual intimate imagery and mandates that social media platforms must remove the content within 48 hours. The Texas House Bill 366 criminalizes sharing manipulated political media without disclosure. In Europe, the AI Act requires synthetic media content to be clearly labeled as such and prohibits especially deceptive deepfakes that could be harmful. In Spain specifically, companies who violate this act could be charged with fines up to 35 million euros. Creating reliable detection frameworks also comes with ethical considerations. Training models requires datasets that contain real human data. Is it ethical to use personal data for improving these systems, and how should this data be protected? Government and tech firms should collaborate to define ethical guidelines that ensure privacy, transparency, accountability, and consent in AI training. Here is just one example of political manipulation through deepfakes. In 2024, New Hampshire voters were receiving calls supposedly from President Biden claiming that their vote makes a difference in November, not this Tuesday, which was the date of the primary election. The call was confirmed that it used an AI-generated voice of the president and was fake, but this could very easily mislead and confuse voters, possibly affecting election results. This case study trained different machine learning models, including CNNs, SVMs, and hybrid CNN SVM models on 1,000 real and fake images and 500 real and fake videos, and analyzed their performance on 4 different metrics: accuracy, precision, recall, and F1 score. The F1 score specifically shows the model's accuracy by averaging the precision and recall rates, which take the ratio of true positives versus false positives and the true positives versus false negatives. The SVM model outperformed the CNN model, but the hybrid model outperformed the SVM model by 5% for images and 6% for videos based on F1 score. Each model has its own strengths. The CNN model was strong at feature extraction from large training datasets. The SVM model was most effective in high-dimensional image classification. But the hybrid model combined the strengths from both models to create the most accurate and robust model. In conclusion, deepfakes present a widespread threat across the internet, impacting different sectors and global public trust. Public confidence and online integrity are increasingly vulnerable to AI-driven disinformation. Some promising detection technologies for combating this issue include EAR SVM, GANs and VAE models, blockchain, and quantum watermarking. EAR SVM stands out because it combines facial feature analysis with an accurate classification system. However, the current detection systems that are available now are often limited by high cost, high resource demands, and low scalability. Making detection systems that are both affordable and accessible to the public is important. We must build a layered defense mechanism in order to combat the evolving threat of deepfakes. By combining technical innovation, public education, ethics, and regulation through cross-sector collaboration, we can achieve this. This work was partially supported by the NSF grant DGE 2146280. Any opinions, findings, and conclusions or recommendations expressed in this work are those of the authors and do not necessarily reflect the views of the NSF. If you would like to contact any of the presenters or the co-authors of this paper with any questions or comments, here is our contact information. And that brings us to the end of our presentation. Thank you.